Thank you. Okay, so you with this misleading title and yeah, so we yesterday we started to talk about similarity theorem and the ergodic context to prove this. In fact, not similarity itself, but particular variant for arithmetic progressions of plane free, which is known as the Roth theorem. And so we introduced some number of tools we started from some basic discussion on ergodic concepts. And so here we finish with von Neumann's ergodic theorem. So this is the result, a statistical result about norm convergence to ergodic covariates for unitary operators, for normal operators. It works also for contraction, but for our applications, normal operators, only 100 nums will be sufficient. And so this is the result, this statistical result. But in fact, as we go through the proof, so we can observe that this is nothing more like the certain asymptotic kind of Pythagorean theorem because of this decomposition due to risk. So this can be interpreted as a Pythagorean theorem. We know that every closed subset of Hilbert space is an orthogonal complement. So and this is the key thing, to verify this result of this average involves the projection into this one-dimensional space of univariate vectors. So that's a nice way of thinking about von Neumann theorem. Originally, von Neumann used spectral theorem to prove this. Only the first. He proved this for unitary operators, and he used spectral theory. But now this is known in more general context, and it will be useful so in proving in many applications, that lead to this nice combinatorial problems. And as we have seen already, one nice application of this is the Pynchon recurrence theorem, which can be thought as a quantified version of Poincaré recurrence theorem. By quantify, I mean that we have this lower bound where this quantum. So in other words, the orbits, from this we can deduce the orbits of the points from E, they return to E. Infinity object. And so we have this lower bound which follows from this pattern. This averages to the projection of the characteristic function, we say E, and where this we have this lower bound. So that's what we. This is Pynchon's recurrence theorem, and I wanted to because the Poincaré recurrence theorem itself can be thought as a certain pigeonhole principle in this measured theoretic settings, but my intention was to formulate this in this way, Pynchon the Poincaré recurrence theorem in this way, because we will see that this is important. This will be important in the context of. So this will fall. This falls, in certain general philosophy of proving this kind of additive combinatorial results by using ergodic theory, and so this is the simplest instance. And so we will see this hopefully at least some part in the context of Sarkozy theorem. Sarkozy theorem in additive combinatorics says that if we have a subset of integers with positive upper density, then we can always find two integers whose difference is a perfect square, or for a given polynomial whose difference is for a given polynomial with zero vanishing zero coefficient with vanishing free term. We can find two integers whose difference is this polynomial. Okay, so now we have to introduce the concept of ergodicity. So it's a very important concept in ergodic theory, which says that if we have so in other words, it says that invariant sets in measure preserving systems and they are negligible where they are they must be essentially a full space. So in other words, we have a measure preserving transformation and the measure space is called ergodic if for every measurable set this condition implies that this set has measure zero where its complement has measure zero. So this definition, I decided not to state ergodicity in this way because it also works for infinite measure preserving systems. Sometimes semi-finite measure preserving systems are important from the point of view of pointwise convergence problems, as the set of integers, for instance, is a certain sense a universal dynamical system from the point of view of quantitative bounds that lead to pointwise convergence. But here we only are focused on finite dynamical systems, probabilistic. You can even think that our measure preserving systems are probabilistic, so we don't need to think. So everything is nice, fine. And so, as I said, ergodicity says that it's impossible to split X into two subsets of positive measure which are t-invariant. So this is what precisely ergodicity says. And so here we have a very nice characterization of ergodicity in terms of behavior of corresponding measurable functions, t-invariant measurable functions. So in other words, if a transformation is ergodic, then the corresponding so then t-invariant functions must be constant almost everywhere. So this is the condition. This condition says that function is t-invariant almost everywhere. Then ergodicity implies that X is constant. And if this condition holds, then the underlying measure preserving transformation must be ergodic. So that's a nice theorem. So today I plan to skip some proofs of, for instance, this kind of results, because I want to emphasize, this. I want to formulate the Sarkozy and show you what kind of tools can be used to prove, and what's the strategy of proving. What's the strategy of using ergodic theory to prove this combinatorial result? So therefore, some of the easy facts from ergodic theory we will skip. For instance, this here is a proof. So if you want to understand this, then I'd be happy to share with this slide. So, but I know that most of you must be familiar with this kind of things about ergodicity and equivalent forms of ergodicity. So here we have forms equivalent. By the way, this is a very nice exercise from measure theory. And so, as a definition of ergodicity, I choose this one, but usually in the literature, when we work with finite dynamical systems or probability dynamical systems, measure preserving systems, then this definition is most common in the ergodic literature. And so here we have nice characterizations of ergodicity. So all these cases, all these statements are equivalent logically in the sense that one can be deduced from the other. And but for our in our situation, we only need to know that what's the ergodicity, what's the concept of ergodicity. So we only need to to keep in mind this informal definition that ergodicity is that it's possible to split X into two subsets of positive measure, where each subset is T invariant. So whenever T is ergodic, this is ergodicity. And so here we have some examples, simple examples, which all these measure preserving systems that we discussed at the beginning here, all they are ergodic. So, and this can be proved. For instance, it's a nice exercise to prove this by using Fourier analysis. Plancher theorem, for instance, it can be used to deduce that the circle rotation system is ergodic, or doubling system is also ergodic. And it's a little bit more of work to show that the continued fraction system is ergodic. A nice exposition is in Ziegler work book about ergodic theory, and where you can find details. But also, a nice exercise from measure theory is to show that circle rotation system or this doubling without using Fourier analysis. With Fourier analysis, everything is very simple and very clean. But without Fourier analysis, one has to do some work to prove that this. And what's important here, Bernoulli sheaf system is also ergodic because it's measurably isomorphic to the circle doubling system, as we discussed yesterday. So all these dynamical systems are ergodic, which is a good thing. And what's also important, if we assume ergodicity for our measure preserving system, then this limiting von Neumann ergodic theorem in this form of von Neumann ergodic theorem, the limit exists. We know that this is projection. In general, we know that this is projection onto T invariant functions. In this case, one-dimensional space of T invariant functions, but we know if underlying space is ergodic, then T invariant functions must be constant by ergodicity. So therefore, if this is constant, then this must be equal to this average. So therefore, here it's a very important thing from the statistical point of view, which says that this time average, so here this can be thought as a time average because here everything is parameterized by this parameter and converges to the space average. So that's what ergodic is. And sometimes some people say that this is some theorem about predicting future because of this inverse. So this is a nice way of thinking about it. And and this is important thing. So therefore, in the class of ergodic systems, which is a large class, in some sense, in ergodic theory, this is very important result. And it's a simple exercise. I briefly describe how to prove this, so you can try it. And so here, another important concept is total ergodicity. So total ergodicity says that we say that the measure preserving system is totally ergodic if for every integer this system, this measure preserving system with nth power of the nth iteration of the is ergodic. So for every n, and then this means total ergodicity. And for instance, presumably the best known example of totally ergodic is the circle rotation system. So one can show that this is totally ergodic because every power is ergodic. And so and here, for instance, but in order to understand, in order to see some systems which are not totally ergodic, these are rotations on a finite space, for instance. So if you consider this space and with sigma algebra that consists of those 4 points, and we consider this measure and we consider shift operator, or this is rotation by 1 modulo 2, then we can easily see that this is not totally ergodic. And in some sense, it turns out that only finite systems, finite in the sense of cardinality, are the obstructions for total ergodicity. So this is some remark, very informal, but one can formalize this, show that ergodicity. If we consider total ergodicity, it only makes sense where systems which are infinite in the sense of cardinality, finite are not interesting. And we will see, that this totally ergodic measure preserving system will be important when we will talk about Sarkozy. And here also a nice characterization of total ergodicity. So this is also some fact that I will leave as an exercise, but so let me. But we need it. We will need it in a moment to derive a nice extension of Neumann ergodic theorem. So it says that we have a totally ergodic measure preserving system. So, or let me put it this way: a measure preserving system is totally ergodic if and only the corresponding coupling operator, which is this unitary operator induced by our measure preserving transformation, admits no rational eigenvalues which are of this form, so which are this unit vectors on vectors from the unit circle other than 1. In other words, we can think that the rationals on the torus, there are no rational eigenvalues from the other. So that's the theorem, and it's one implication is very simple. The other is a little tricky, but if you think a little bit, then you will. So it's a basis to consider the functions of this form and to see that if we assume that our system is not totally ergodic, then we have to find a function which is non-constant, and at some point we consider the functions of this form. It turns out that this function must be non-constant, and we obtain a contradiction. So because it turns out that fj is an eigenvalue, eigenfunction corresponding to eigenvalue of this form, but we assume that this kind of elements cannot be eigenvalues for our coupling operators. That's how we do it. But I skipped it, and I said just we want to derive more interesting things. This is just a technical result, but it will be important here in this theorem. So in the extension of from Neumann ergodic. So this extension says that if we have a measure preserving system and a probability space, then the total ergodicity is equivalent to the fact that for every square integrable function and for every integer student R, we have this convergence. Okay, so in other words, so here we see that we consider more complicated orbits, not along integers itself, but along arithmetic progressions of space in Q. Okay, so and then the same conclusions. So this is important result. So in other words, linear polynomials, orbits along linear polynomials are good for norm convergence of ergodic convergence. So that's an important result. And here we can see the proof. So this is if and only if. And here one of the ingredients will be this theorem. So let's take a look one more time on this result, and we will use it to prove this characterization of total ergodicity in terms of convergence, ergodic convergence. So let's assume that we have this. So the first implication would be assume that for every square integrable function, this limit exists for every Q and R. Okay. So, and if our system, and suppose for a contradiction that our system is not totally ergodic, so which means that there exists an integer Q and non-constant square integrable function, which is eigenfunction for our Koplan operator. So in other words, this equation holds. And then, if this is the case, then if we use this convergence, then from this invariance, we see that this average is constantly equal f of x. But on the other hand, and we know that this function is inconstant, but on the other hand, by this condition here, this converges to a constant, which is the integral of f. So therefore, we obtain contradiction because we assume that this is non-constant. So that's definitely the implication in one direction. And so now we have the other direction. So suppose that this system is totally ergodic and f is square integrable function and Q and R are integers. And now if we apply an inergodic theorem to this, so then total ergodicity means that these powers of T and the power of T are ergodic. So therefore, so in particular T to Qn is ergodic. So now if we apply the von Neumann result for Neumann ergodic theorem, classical von Neumann ergodic theorem, so then we see that this time average along this orbit converges to this space average. And now using the fact that mu is T invariant, then this average is equal to 3. That's how we get this implication, assuming total ergodicity, how we get this statistic, this extension of von Neumann ergodic theorem. So this will be important in a moment. You will see that this will constitute a first step of certain induction that will lead to deduce Sarkozy. And now let me change the topic a little bit and present a very important inequality in ergodic theory. This is an inequality, this is van der Kolk inequality, which is formulated for in the Hilbert space setting, but in fact, this was invented by van der Kolk in the context of his van der Kolk estimates for exponential sums and equidistribution theorem. So van der Kolk gave an alternative proof of Weil equidistribution theorem for polynomials. We know that equidistribution theorem says that we have a polynomial which has at least one irrational coefficient, then it's equidistributed modulo 1 in the unit interval 0, 1. So this is the famous result of Weil. And Weil originally proved this by inventing Weil's inequality, an important tool in analytic number theory, but van der Kolk then observed that in fact certain nice induction can be employed by inventing this kind of thing. In fact, this kind of inequality, but in the scalar set, on the set of complex numbers. But it turns out that if this van der Kolk inequality, sometimes it's called van der Kolk tree, can be extended to this more general Hilbert space setting. It's a very robust. So here is a very robust inequality. So I like to formulate this in this form. So this is this finitary form, which by manipulating with choice of H, we can deduce this function. But on the other hand, this is also a very nice criterion to say something about the convergence. Okay, so this is a very important criterion saying that if we have so if we consider a sequence of elements in the Hilbert space, and we can think that this is a bounded sequence, and if we consider this this sequence of scalars, and if average of this sequence converges to zero as h goes to infinity, then the average of UMS converges to zero in a Hilbert. Very, very nice result. So we will see in the context of Sarkozy and Roth how this can be, how effective it is, to prove some interesting results, and how this at this moment, we can appreciate how powerful van der Kolk's inequality is. But in a moment, hopefully, I will be able to convince you that this is very, very robust result. And in fact, as I said, we prove this much stronger quantitative statement. So this is, which is of this form. And I personally like, to think about van der Kolk in this way, as it has many applications, in number theory and history harmonic analysis. But but for this application that we'll discuss today, this form is, will be just perfect. But in fact, from the proof, we will see that we prove this. We provide this upper bound for this average. And as I said, by appropriate choice of age, and we can see that H is smaller than n, and with passage of limits in appropriate order, we see that it's such. As long as this supremum is fine. As long as, in other words, as long as we work with bounded sequence in the Hilbert space. Okay, so let me show you. This is just, this is what is the most important. The trick, in order to prove this, is to observe that this average can be this additional parameter and corresponding to this number h can be introduced by certain averaging trick, which is which follows from the fact that the set of integers is translation invariant. So this is what we do. So we can interpret this average as a sum from a sum over all integers, where okay, so let me write one sentence here, and it will be clear what we do. This is what we do. We start with this average. So this is here we use this convention from combinatorics that is in this level and integers. And here we have UN, and now we can see that this can be interpreted. This is by the definition the average from over C, and here we can have this characteristic function, and now we can put the average over H, so up over N H, and so let's start this. Okay. Okay, this is N, this is H, and now everything, because of, so this average can be put for free because this is independent, this is just one here, this is independent of H, and now by using translation invariance, we can add this H here as well as here in the argument of the characteristic function. This is n. This is I hope that. Yeah, so this is what we do, and this is the Van der Kolk trick, very important, and it arises in many places in ergodic theory and in number theory. So, and that's the key idea, I would say, in this key observation, improving this result. And once we have this, then the other things, this is just appropriate splitting of this sum, because we want to match the parameters efficiently, and then this is other than that we use Cauchy-Schwarz. So therefore, this is what we do. So here, now having this sum, we want to. So we split, this sums. These are in fact both finite sums, and we split, into the pieces where some pieces which will have precisely H elements, and the other piece, the main piece, which has this form, because we want to remove H from this picture. And by triangle inequality, I think. So let me see. Okay, so this is the sum that has H elements. This is also the sum that has H elements, so therefore they will be they will enter into this error term, and this is the upper bound for this for our sequence. We assume that this is bounded. H is always chosen to be smaller than n, and so this will be the main term, which now we see that is dominated by triangle inequality by, and this guy corresponds to this, and now yeah, because we see that here this element and this element, if we took the norm, then they are bounded by this quantity. And okay, so let me speak. And this is from here, you see that it's clear that if everything so the splitting is because we want to remove this H from this characteristic function, and now we can do this because we have H here and H here, and we want to leave it here, on this element. Okay, so now we have, this is, we end up, with this, and now we have to take care of this. This is the error term. This is the exactly the element that is good for us, and we have to now understand this graph. So for this purpose, we do Cauchy-Schwarz, and by Cauchy-Schwarz we can, because everything is probabilistic here, so we can use Cauchy-Schwarz. We can insert the norm here, and now we open the square. So this is the expression of this form, and now this is what we do. So by using some symmetry, this is dominated by this, and now again. So what do we do here now? We change. So here we change the variables. I think, and we also, because this is, so here the set of this set is translated by H1, but H1 is at most H, and we want to have, instead of this set, we want to have n itself. So therefore, we translate everything in a way that we sum over n, but the error term produces this term here. So therefore, if we do this, then so we end up with this, which falls from the change of variables. So that's how we get this inequality. And now from this, so now we see that, so therefore this guy is controlled by this. So therefore this is what we proved. is the inequality of this form. This is essentially what we want. This is the expression, in van der Korkut, in our assumptions, that is nicely controlled in the sense that this is the sequence that whose average over H converges to 0, and so now we have this. This is essentially this quantitative form of van der Korkut. This is what I stated in the remark. And now this is simple matter. So first we pass with H. Hold on. Now we first pass with n to infinity, and so we choose H that this quantity is small, and because this converges, we remember that the average of SH converges to 0, so therefore we can always find H that for sufficiently large H, this will be as small as we want, and this small is controlled by this epsilon, and also because this can be also made sufficiently small for sufficiently large integers. So therefore, we have now, if we use this inequality, that we have this, and so therefore, in other words, we can think first we pass to infinity with H. With n, sorry, and then we pass with H to infinity, and in fact, this we obtain this. So that's the van der, that's the conclusion of the van der Korkut. So this is here. What's important is the result of this form. So that, in other words, if we assume that we have this and this converges to 0, then the average is corresponding to the vectors in question. Bounded sequence of vectors converges. And okay, and now on the first application of this, it's a theorem of Furstenberg, I believe, which is a polynomial extension of von Neumann. So now you see that instead of working with polynomial instead of working with linear orbits, we consider polynomial orbits. So here, we take orbits along Pn, where Pn is arbitrary polynomial with integer coefficients, and we, assuming that P is totally ergodic, we have that this time average converges to space average in open. So that's the result of and now, so in order to prove this, we will proceed by induction, and the key ingredient will be van der Korkut lemma, this van der Korkut trick that we have seen in Hilbert space. So, and in order to see this, so first of all, observe that if we want to prove the results like this, we can assume that our function f has mean 0, and we only, because if we subtract, the integral from both sides of this inequality, then this the resulting average will converge to 0, and the corresponding function f will have mean 0. So this is the first reduction that we, and we assume that. And we can assume also that the degree is bigger or equal to, because for the linear polynomials we have already verified this result. So this is the result here. So this convergence is equivalent to total ergodicity. So and under total totally ergodic measure preserving systems, we have this. So this verifies Furstenberg result for the linear polynomial. So therefore we can assume that our polynomials have degree at least 2. And so this is now what we do. So we can assume that un, these are vectors of this form, and we have to show that this average converges to 0 in L2. And this is precisely what is in the conclusion of van der Korkut spaces. Okay, so this is now, so we want to derive this conclusion. But we can do this if we use this criterion, if we show that the average over SH
converges to zero as h goes to infinity whenever sh is lim sup of this expression. And so therefore we have to verify this condition now. And this is very simple if we use induction, because now let's take a look at this. So we have to show that the average over n of this lim sup of the average of this expression converges to zero. But now we can observe by the fact that t measure mu is t invariant, that by the definition, this expression, this is the scalar product of those two functions. And but in other words, by translation, by the t invariance of the underlying measure mu, it is the scalar product of this. And here, the good thing is that we obtain t raised to the power, which is of this form, but we remember that this is polynomial with integer coefficients. So therefore, if we started the polynomial of degree, let's say d, then this polynomial has degree d minus 1. So therefore, we increase the step. So therefore, q now is a lower degree polynomial. So therefore, we can apply induction hypothesis. And by induction, we know that our theory is true for all polynomials of degrees smaller than d, let's say, and than our original polynomial. So therefore, this converges to zero. And now, so if we know that this converges to zero in L2 norm, so in order to deduce that the average over these expressions converges to zero, we have to only use Cauchy-Schwarz inequality. So, and this is what we do. So we see that if we average over n here, so this converges to zero, therefore the scalar product by Cauchy-Schwarz must converge to zero either, and therefore this limit is zero, and this verifies the assumption in the van der Korthout tree, and so therefore having this and using van der Korthout lemma, we can deduce that this average, which you remember un is of this form, converges to zero in L2. And this is what we have here whenever f is this is the convergence here in this display whenever f has mean zero. So that's how we obtain this polynomial extension of this is the Furstenberg result. This is the extension of von Neumann to totally ergodic system. This is also true if we go beyond. This convergence also is true when we go beyond totally ergodic systems, but then we can identify what limit might be. It doesn't necessarily need to be constant, but the convergence also holds. Okay, so and now here you see that we have an extension of Khinchin theorem to this polynomial orbits for totally ergodic systems. So this is the extension of Khinchin and Poincaré to polynomial orbits. So this is we can think of this as the polynomial Poincaré recurrence theorem, which in a moment will play an important role in the proof of Sarkozy. But the key thing here is that so this will be, first of all, we will do this under assumption that our measure preserving system is totally ergodic. But in order to apply this to derive this combinatorial applications, we need to know that it holds for ergodic systems or at least ergodic systems. But in fact, we prove that it holds for all measure preserving systems. But ergodic systems are fine if we are familiar with ergodic decomposition. So that's therefore, ergodic systems, measure preserving systems, is a fairly useful and large class of transformations and these combinatorial applications. If we prove something for ergodic systems, then we are happy. But now, so first of all, start from totally ergodic systems. I tried to build some to show you how these things were developed, and whether the differences in different systems. So in ergodic theory, it's important to be familiar with examples. So this is some theory of examples, in my opinion, like harmonic analysis also. So if we have good examples, then we can understand many things. But and here is some, I believe, some illustration of this, where we build some theories, proving for some classes and then complicating objects and trying to see if we can deduce similar conclusions. So okay, so let's try to deduce this. And here the scheme will be very similar to the proof that we have seen in the context of Khinchin's theorem and this quantified version of quantum. So this is what we do. We know that now we have norm convergence by the previous theorem. So in other words, this time average converges to the space average, which is the measure of A. So therefore, by the, for instance, dominated convergence theorem, this scalar product converges to this, which is the measure of A squared. But now this, what we have here, if we okay, so let me put it. So now we observe that this, what you have here, this is the scalar product of those two functions, characteristic function of A and characteristic function of A, translated by this function. And so here you see, therefore now if we integrate this, then we see that this average converges to this, and now we are done, because if we take n sufficiently large, then we see that we have this lower. And of course here, in order to to make sure that this lower bound is meaningful, we have to assume. So of course, this inequality works under these assumptions for measurable sets, but in order to deduce something interesting, about the recurrence, we have to assume obviously that a measure of A is positive. Otherwise, this is useless. But for positive set of positive measures, that this becomes meaningful and we can deduce something about recurrence here. So, but in general, we have this nice inequality. And now, so we prove this, for totally ergodic systems under this assumption. So, and sometimes, this is, so the totally ergodic systems, as we'll learn, next time, there is some hierarchy, that we have strongly mixing systems, weak mixing systems, totally ergodic systems, ergodic, and general and measured preserving transformations. And the strong implies weak, weak implies mixing implies total ergodicity implies ergodicity, and they all are strict implications. They cannot be reversed. And here, so therefore, we would like to remove this assumption about total ergodicity from this correlate, and we would like to prove an extended version for all measured preserving systems. So if we would like to prove this reason. So in other words, the genuine polynomial quantifier recurrence theorem says that for every measured preserving system, only measured preserving, and for every set, measurable set, and epsilon and polynomial integer coefficients with which is 0 at 0 with vanishing pre-term, there exists an integer such that this inequality holds. And also, because we work with arbitrary polynomials here, we assume that T is invertible whenever P takes negative values to make sure that this definition is meaningful, that it makes sense. Okay, and that's our aim, to prove this for general measure preserving systems. And here we will proceed. And here is what this is our aim. We would like to use this theorem to deduce Sarkozy-Furstenberg, which is So in fact, because of the first correspondence principle, this result, this polynomial Poincaré recurrence theorem, can be thought as as this combinatorial result on the set of integers. So Sarkozy-Furstenberg, it says that if we have a set with positive upper. Okay, forget about banner because we only use the upper banner density vector, upper density vector. So this is also true for upper banner density vector. If we upper banner density is a little bit more general definition, require a certain uniformity vector. So for if A is a set with positive upper density and P is a polynomial with integer coefficients with vanishing zero term, and so then there are pairs of elements in E with the property that x minus y is equal to P of n. So in other words, if we think that P, we can think that P of n is n squared. So therefore, Sarkozy original result says that in this sets with upper density, with non-vanishing upper density, we can find two pairs of integers whose difference is a perfect square. So that's the result. And yeah, so as I said, so here if we think that we know that, so let me recall this discussion that we had yesterday. If we seek these configurations here, then this is the same as this can be interpreted in terms of shift operator. But we know that the shift operator that we know that as we have already seen, as we have already discussed, the recurrence theorems are not truly sigma infinite dynamical system, infinite measure preserving system. They are all true infinite dynamical systems. So therefore, an additional ingredient is needed, which is the Furstenberg correspondence principle, which is a certain, provides certain bridge, between this ergodic world and additive combinatorial world. But it can be done, and therefore, because of the Furstenberg correspondence principle, this polynomial Poincaré recurrence theorems, in fact, this Sarkozy-Furstenberg theorem implies Sarkozy-Furstenberg. But now, but we will in a moment, we'll formulate, maybe tomorrow actually, we formulate the Furstenberg correspondence principle in a way that can be applied to this problem. But let me emphasize that now what will be the strategy to pass from totally ergodic to ergodic systems. And here another decomposition is needed. So all what we do are certain Pythagorean type theorems. So we can prove something for a certain class of functions. Let's see, let's span, closed subset, which has this property for which we know that some property is closed. And let's take a look at the orthogonal complement. So that's the strategy. This is kind of Pythagorean type of result. And here, this is what we do. So we will split our Hilbert space into two closed subspaces. One, this will be totally ergodic component. The other part will be rational spectrum component. So here we have definitions. So rational spectrum component, this is the set closure of the set of the form that that F is an eigenvector with eigenvalue 1 for certain power of Koplan operator, and totally ergodic part. These are the functions that this limit is equal to 0 for all k. And so now we can observe that if we work with measure preserving system, which is totally ergodic, then this part consists of constant functions. And on the other hand, this part here contains every function integral zero. So that's a nice thing, in the situation of totally ergodic systems. But now we want to go beyond that setting. And so our aim is the following proposition. So we have to show that L2 space can be decomposed in these two parts. And so let me show you how the proof goes. So this is what we do. So we take function f in L2 with the property that for certain k, this identical. Okay, so and now let's take G running from TA, and we have to show that this guy is orthogonal to F. So this is what we do. Take a look at this, and now by the fact that the underlying measure mu is translation invariant, we have this, and the fact that this function is TK invariant, we have this, and we can iterate this. So therefore, we end up with the identity like this, and the scalar product here is equal to this for any k and n. In fact, sorry, for k like here and for arbitrary n. And now we average over n, and we obtain this. And we use now Cauchy-Schwarz inequality, but we know that this function g is from HTE, so which means that the norm of this guy, this average, converges to 0. So therefore, this by Cauchy-Schwarz converges to 0, and now we see that, so therefore, this space here must be contained in the orthogonal complement of this. So that's the one inclusion. And now, in order to show the converse, so this is what we do. Oops. Okay, so we take f, which is orthogonal to the rational spectrum, so which means that this is orthogonal to this space, and we want to show that it belongs here. Okay, so therefore this means that for every k, so this space contains the invariant subspace ik that consists of tk invariant functions. Okay, so therefore f is orthogonal to ik for every k. So in particular, we have that this scalar product is 0 because 1 is in particular eigenvalue. So therefore, by mean ergodic theorem, if we consider this average, by mean ergodic theorem, this converges to this. But here we see that this integral is interpreted as a scalar product function constantly equal 1, which is 0 because of this. So therefore, this implies that f belongs here, and then we have this inclusion. So therefore, if we combine this and this, then so and that's what we want, because we have shown that the rational spectrum, the orthogonal complement of rational spectrum is equal to, in fact, the ergodic, totally ergodic component, and so therefore this proves this decomposition. So and now once we have this, then we can prove polynomial one-parallel recurrence theorem, but maybe I'll stop here, and we will start tomorrow from this proof, and then I'll show you how to implement the current correspondence principle of Furstenberg to finish the Furstenberg-Sarkozy, and then we will have some idea how this ergodic methods works, in the context of Sarkozy, and we can start to talk about Roth, which is a little bit more complicated and will require more concepts, but this will be our thing for tomorrow. Thanks.
The question?
Maybe just so in this polynomial recurrence, you also have the ends where this is true is synthetic.
Yeah.
And you can do the double averaging, kind of the uniform averaging.
Yes.
Yeah.
You can do this. That's right. Yeah. And that's very important. But for the purpose of this lecture, I wanted to avoid all this fancy notions, because this is what we. But syntheticity is a very important concept. I even avoided to use this name, but that's it.
So in the ergodic theorem, can you take orbits primes?
Yes, you can do also along primes, and yes, and for instance, the norm convergence. Okay, the proof. I haven't seen a proof of norm convergence along primes. I haven't seen a direct proof, but this follows from Mattes results, for instance.
No,
Or
but,
pointwise.
but
If you
it,
use
it
pointwise,
follows
pointwise.
from simple, because here we are talking about mean convergence.
Yeah.
So there is no need for that. And then it follows from the prime number theorem. Because so you need to use the spectral theorem. And what you need is the prime number theorem in arithmetic progressions and Vinogradov's uniform distribution result, and then follows for primes. But there is no recurrence result for primes. It's prime minus ones and prime plus ones.
Okay, so in other words, but so in this proof you use a little bit of technology from the.
Or much more than here.
Much more than here.
Yeah,
Because
much
here
more.
this is very.
Yeah.
Very soft, right? In
Yes,
the sense of
I agree.
based on this.
And that one is not soft.
But primes they require.
Yeah.
Vinograd.
The exponential sign, yeah, you need a cancellation. That's
Which is, originally why, so, when he proved his distribution theorem, he also, this is how he developed, by inequality. So, but, then this, later on by observation of van der Kolk, I think that, this is what we know in our textbooks, is all these proofs are by this differencing, but originally it was by inequality. And this is very interesting, to take a look at this original paper. I was impressed, how he built this, because he obtained, in fact, even much better bounds. He didn't, use this divisor function that produces n epsilon from the by inequality, but he counted some lattice points in some, some sets that arise, in this process of differencing, and he was able to obtain better. But if you want to use, by inequality, for instance, for this, the one that we have this n epsilon loss in front of the wild bound, then you can derive directly equidistribution theory. So that's a trick. So he was much more careful, so that is interesting. But I think that it was forgotten by because of van der Kolk and this much simpler approach by using this differencing and induction, which reduces to Weil criterion for fractional part of alpha n.
And I think there is even like a prime power, even the result like that. So if you take n to be a prime in that capital P of n, there is still theorem. That this is still there's still an analog of right?
Yeah.
But for convergence.
For
not
convergence, not for recurrence.
for recurrence.
Yeah, for convergence, yeah. Like converging, pointwise convergence, yeah.
And a polynomial of primes.
Yeah. Yeah, because then you use
That's
two
what
as even more. Interesting.
Questions, Max?
Yeah.
Functions,
But if polynomial,
the right hand side,
of course,
this is
p square
this is the best possible.
yeah.
Here? Yes, I think it is. Because here you have two terms. You have more terms, k terms, then you have k power. This corresponds to. So you will see that in the context of raw and context of more general arithmetic expression, then you can have k plus 1, because k comes from the fact that you have arithmetic regressions of length k and plus 1 because you pair with the characteristic function, so therefore you have to compensate.
Max, questions? Yes.
Extra independent. Is it like so if you have if you have two terms, yes, like you the measure the probability of the intersection is like the square root and the square power.
Right.
But if you have A and B, can you say that for any if you have A and B
Here and here?
I mean, and then you have A intersected with T minus
Yes,
T
Ah.
and B. And then
Good
you
question.
then mu
I
A,
don't
mu
know, I
B.
don't know, I don't know.
I mean, in general, it cannot be because B, if you have a non-ergodic system, then B can be in one component, A can be in another component, and the iterates or the inverse images of A will never intersect B.
Yeah, but
So,
it's
but if you assume ergodicity, that's what you're asking, right? So instead of having A and A intersection e to the minus P and A,
Yeah.
you replace the A by B.
One of the two, yeah.
B, but then it cannot be for a non-ergodic.
Non-ergodic.
If it's ergodic, maybe. Actually,
If it's
probably
really mixing,
totally
it's for
ergodic.
sure, yeah.
You know, the other
If it's
way
really
of
mixing,
thinking
it's
about it is
definitely
about
true.
certain kind of independence, right? This tells you that this events here are somehow asymptotically independent, or this independence arises infinity many times in this sense. So, yeah, I think that this is the right way, of quantifying, presenting, Poincaré recurrence theorem. Not like this principle like we started yesterday, that this is some pigeonholing, saying something pointwise, but it's statistical. It's much better because it has not much nicer, applications, in this combinatorial, to this combinatorial problems. And we'll see, tomorrow how important it is. Thank you.
Other remarks, questions? That's all for the discussion, and it's still here. So we will now.
Uscito sottofondo riconosce il marchio di per tipo di stata con